Okay, questions for?
Okay, thank you, Eric. I think I agree with most of your positive account of how these things work. I just want to ask you a question about one aspect of it, about a theory's domain of applicability. You said two things that actually don't seem to me to be consistent with each other. One is that a theory's domain of applicability depends on the level of approximation and precision that we demand of it. And the other one is that it changes with time as our experimental technique improves. And those strike me as related but different things. So for example, if I'm questioning, is Newtonian gravity applicable to Mercury? Well, if I want to know where to look for Mercury with my binoculars, then yes. And the GR corrections are negligible, and that is true even though there exist observations for which the GR corrections are needed. And the reason I'm pressing on this is that the relation for such and such a level of accuracy, the theory, these things are within the scope of the theory. That can be a timeless relation, even though, of course, our knowledge of that relation changes with time. So, which of the two did you mean?
So I think you're absolutely right to press me on this. So I guess I want to say that I don't really like reifying theories at all. So I think that in some contexts and for some purposes, it's right to say that Mercury is captured quite adequately by Newtonian gravitational theory, and in some contexts and for some purposes it's not.
Right.
I think of Newtonian gravitational theory not as referring to one fixed thing. It's a term of art whose meaning is supplied in large part by the context of the investigation that one is actually involved in. So but of course, I'm not just a complete wild relativist about this. Not anything can count as Newtonian gravitational theory. There is, I don't know, I'm not quite sure I want to say a Lakatoshian solid, heart or core, but something like that. There's obviously just some stuff that is just Newtonian, no matter how you slice and dice it. And there's just some stuff that's not. And then there's a lot of gray area.
You're next.
So I want to thank you for this talk, and listening to you kind of seems to me to turn the problem on its head that I was worried about, which was paradigmatically when one says that in quantum mechanics we have to be able to explain observation and measurement within the theory, and we don't know how to do that. And what you need is something highly theoretical: unitarity, linearity, blah, blah, blah. But another way to think of schematizing the theory is that the theory is in a way emptied without being realized in something else.
Yeah.
And this is actually how Kant thought of schematism, that the understanding is just empty. It doesn't actually say anything or have any significance, so it's at most logical, logically consistent perhaps. But schematism means you have to find something else to realize it in that has more richness, as it were.
That's right.
Which for him would be spatial temporal intuition. And some of the quote from this one.
I cut out all the Kantian stuff.
That's when it's in the ellipsis.
But there was something you had before this, which made me think of this turning thing on its head. Was there a previous quote from him? It was much more, anyway, it doesn't matter. But the idea seemed to be that, here. It's impossible to understand the theory if we had no systematic way to put the theory into connection with observation or experiment.
That's right.
Meaning, we don't have to represent experience within this very clearly understood theory. We have to project theory into this less clearly.
That's right.
In order for it, that's what schematizing is.
I think that's exactly right. That's how I think of it. Yes.
Jim, you were next.
I think I'm maybe going to be a little less serenic than Wayne. I'm not entirely sure I do agree with everything you said.
Bring it on, man.
Well, there's something, there was a positive part and a negative part to the talk. I'm not entirely sure how to disentangle them from one another. But the negative part seemed to me to be tilting at windmills a little bit, or attacking a straw man, or whatever.
And I said I agreed with the positive part.
Yeah. You did. But I said I don't know how to disentangle them. Okay, so I take it that no reasonable person believes that we are presented with some formal apparatus and told to assent to its truth about the world without having more to say than
You've read the
just
scientific image, right?
What's that?
You've read the scientific image, right?
I said reasonable person. So I think that the picture that you're like the view that you're arguing against, where when people talk about formal theories or representational capacities, or someone ever say something like that, I mean, I think that we get to that after a whole lot of hard work.
That's right.
And we're able to reason about it in a reliable way only because we've learned how to use the theory successfully. And when I say we, I don't necessarily mean us individually, but also our forebears and so on. But Maxwell's theory, for instance, is something that took us, like a century to get to, more obviously, and that we still didn't understand for a century after that, at least. And of course, there's some sense in which we do know everything there is to know about the solutions to any linear hyperbolic system, right? Just we've got all the fundamental solutions, and can't you just integrate them? But it's also the case that they aren't just symbols on a page, right? I mean, these are like mathematical descriptions of things that we know how to think of as physical objects and that we've learned how to experiment with and manipulate and so on.
I think you're so far everything you've said I completely agree with. Insofar as the standard view gets anything right, it gets it right only because it is relying on this history of extraordinary detailed work in learning how to bring this mathematical formalism into fruitful substantive contact with the real world through trial and error and experimentation. And actually, the example of Maxwell's is I think really lovely, because I think that the example of Hertz's search for how to produce and how to measure quote unquote free electromagnetic radiation is a beautiful example of this. When he started out, he had no idea how to produce or measure free electromagnetic radiation. He had no idea really how to, neither experimentally nor he had no idea how to theoretically model what an experiment would look like that was that would be a positive, that would adequately and appropriately represent an experiment in which electromagnetic radiation was actually measured and detected. I would actually claim at that point, Maxwell theory, the epistemic content of Maxwell theory did not contain an understanding of electromagnetic radiation. It was through years of trial and error, of constructing theoretical models, playing around with instruments, trying to figure out how they fit together and work, that eventually led to the real understanding and grasping of electromagnetic radiation as part of Maxwell theory. And the epistemic content of Maxwell theory was enlarged. And at that point, they could then stop and say, I'm now going to, we have the Maxwell equations. I now know how to write down solutions that it makes sense for me to think of as radiation. I have an idea of the experimental of the interpretive principles that I'm going to use in kind of the standard use sense to talk about this as radiation. That's all well and good. But we can't forget that I would claim that up until that point, none of that was even part of the theory. None of that was part of our understanding and comprehension of the world that the theory gave us. And until such time as the theory gave it to us,
Eric, the idea that light was a variety of electromagnetic radiation didn't originate with Hertz only after he did the experiments. I mean, so
that's right.
This is something that was part of the theory from much earlier, and that Hertz certainly deepened our understanding of it. But in some sense, I think that that's all beside the point. The issue that I'm trying to join is whether you have just endorsed the standard view.
I think that's right.
Yeah, and no, I haven't. The standard view, if one likes, is a wild idealization that is useful in certain circumstances. but that is not at all an adequate and appropriate account of scientific knowledge in anything like its richness and complexity. It certainly is useful for certain kinds of foundational and philosophical tasks, but it is not adequate and for an accounting of scientific knowledge.
Well, then let me suggest that you're not,
as an idealization, it's sometimes incredibly useful.
you're not using your own view of scientific theories as a way of understanding philosophical theories. So, sure, there are ways in which we present how we as philosophers or as mathematical physicists think about our theories that has buried in there a whole lot of information about what we're idealizing, when those idealizations work, how we should think about the actual applicability of the sort of the formal parts or whatever of our theories to actual scientific practice and so on. But to neglect all of that is to come to the philosophical views in a way that I think misses important content and is ultimately misleading.
So I'm not sure I understood the last few sentences. Can you repeat what the lesson is? I'm not sure I got it.
Let's talk about it over drinks.
Okay, you're next.
Yeah, so one of the things that was really beautiful about the way you presented that, of course, was it was this lovely old-fashioned way of presenting it, where we don't do all of this annoying, messy stuff that we tend to do in the contemporary world, where you link it to everybody else who said stuff like this, right, and connect your view up. And of course, it was a much prettier talk for that. But of course, there's loads of echoes of things that get said in the philosophy of science community here. And what I think is interesting about them is some of them, you know, aren't things I think philosophers of physics tend to be terribly keen on, and I'm not even sure you would be, right? So, I mean, Nancy Cartwright's an obvious example. I mean, all the talk about modelling.
Nancy Cartwright is totally wrong, by the way.
Well, so I thought you might think that, but then, you know, but I mean, philosophers of physics seem to have a default position that Nancy is wrong, right? But you know, I mean, Mark Wilson's another person, but I suspect
More interesting, but still wrong.
People, you know, philosophers of physics like Mark stuff better, but yeah, Hasok Chang is writing
Even more interesting, but still wrong.
Hasok Chang's writing a book at the moment. So this is kind of unfair because he was like had a reading group in London, but he's writing a book about kind of a pragmatist theory of knowledge, and part of his point is a lot of our knowledge isn't propositional, and he tries to link it up to the epistemology literature on knowledge how. And the reason I'm mentioning all of this stuff is that when you work out the details of any of these things, I think that you're going to get into stuff you would hate to be committed to, right? So, for example, it's obviously in some sense it's got to be true that our knowledge isn't all propositional, but then when you try and work out what that implies, you end up saying things that look very contentious. And likewise, of course, it seems it's got to be right. We don't have perfect models of anything, and it's all about modeling practice. But of course, what Nancy does is take that to the next level, and then we tend to not like...
And that's exactly where Nancy and I part ways, is when she says that's all models. And I'll say, no, of course it's not all models. There's a theory here.
Yeah, of course, but of course you can see where she gets the pressure, because you have to... I mean, part of the problem is that when you work out the positive side of this, right, she has to say what we do have knowledge of. And when you say, yes, our knowledge is messy and it's patchy, if you want to go further and you want to say what kinds of knowledge we do have, you often end up saying something like what Cartwright says, right? So you end up saying we have knowledge of like local causal powers in systems because of individual modeling or something. And then none of us like that. So I'm sort of wondering whether you have anything to say about some of the ways this might be developed or extended such that it would differentiate
Yeah,
between
so
projects.
honestly, I suspect that I would actually have a lot of sympathy for what Hasok is doing, given this past work and given conversations I've had with him. I'm a pretty hardcore committed pragmatist in kind of Peircean and I would claim Carnapian tradition. So I have no problem whatsoever with pragmatic accounts of truth, reference, knowledge, that sort of thing, and that's exactly what is behind a lot of this. I will definitely differ, though, I think, from people like Nancy and probably Hasok as well. For instance, I thought JB's talk was beautiful and actually gave us some real insight about the world, about how general relativity, what general relativity can and can't tell us about the world, or what it may tell us about the world. I strongly suspect that neither Hasok nor Nancy would have much patience for JB's talk because it's so abstract and so
If they had heard it, they would convert.
So it's not, again, I'm not demanding that for every argument we give in science and every knowledge claim we make, you always have to have this picture of the experiment in hand. No, this is what's in the background. This is what this is what's this is what's bedrock. This is what has to be there in order for us to understand theories as theories about the world. And then once we have that in hand, we can do things like what I think Jim was suggesting, and that I would claim JB was doing. Give, in fact, very formal and abstract and high-level arguments about the mathematical structure of the theory, and gesture at and point us to what kind of understanding that certain features of the mathematical structure of the theory can tell us possibly about how the world actually may be or may not be. So I'm not sure that directly answers your question, but I was giving it my best.
In my lineup of things I'm trying to keep track of, Rob, you were next.
Okay, thanks. I thought it was a great talk too. I also agree with a lot of your criticism of existing views of how theory and observation relate. I was just a little bit unsure about how to connect this notion of the schematic observer to what you were saying about the interpretation of theories. Mm-hmm. Because I feel like there's something that Stein was trying to say with these remarks that to me didn't come out. I mean, I never liked that line about, to interpret a theory is to explain how the world would be if it were true. Because if quantum mechanics is true, then the world would be like this. Right? This is how the quantum world is. But from the point of view of what the theory is telling us and how do we interpret the world as quantum, right? What I think that means, and I think I got this idea partly from Stein, partly from Dimopoulos, but it's to understand why we think the world has to have a quantum mechanical structure. Why do we think our experiences are impossible to embed into a classical structure? And that involves something highly schematic, right? So, for example, someone really knows how to operate a Stern-Gerlach device. I don't. Or maybe I might know how to operate the thing with polarizers too, right? The Aspect experiment or anything like that, and not know how to operate the Stern-Gerlach device. Or I could be someone like the person I actually am, who could begin to think about how either device works, but can get a sense of why the outcomes of these experiments exhibit entanglement, and why I can't embed these experiences into a Newtonian picture. And of course, that's not a new problem it's not a new issue with quantum mechanics. It's highly schematic, but in a sense it always was, right? If I were Eratosthenes, and I'd figured out how to tell what the size and shape of the Earth are from various kinds of observation involving a very schematic picture of what the stars look like at different points on a sphere, I could actually write that down in such a way that someone who lived antipodally from me, right, could do the same thing and convince herself that it was also, that she too lived on the same sphere. And all of this involves what I think Stein meant by this notion of a schematic picture of how the observer is able to understand some features of the world that are theoretical. I hope that is friendly to what you were trying to say.
I think it is. To me, the way that you began your question by saying you weren't sure how on what I was saying, where the schematizing the observer entered in connecting the theory and experiment. And I think the kinds of things you sketched are exactly the kinds of things I had in mind. The way that we met the thermometry is an extraordinarily rich and, for instance, is extraordinarily rich and complex field, a discipline of experimental physics. How it is that the kinds of detailed knowledge one has to have of a given type of thermometer under given conditions for measuring the temperature of particular kinds of fluids is really, really extraordinarily detailed. But one doesn't always have to give a very precise model of a particular kind of thermometer when measuring a particular fluid and under particular conditions for particular purposes. But one has to know that one can do it. And the fact that we know how to construct the models of the thermometer itself and its very complex interaction with the fluid in the immediate vicinity of the thermometer is part of why we think the thermometer is measuring the temperature of the fluid and not who knows what. So it's schematizing the instrument in this case is what allows us to say that, that tau in the Navier-Stokes equations is temperature of the fluid, because I know how to mediate between the complexity of the fluid and the formulas in the theory by making these models of the thermometer. I think that is consonant with what you're saying, and perhaps friendly with what you're saying, but I'm giving this description to try to make sure that I understand what you're saying and that how I'm thinking about it fits with what you're saying. So are we grokking each other here, Robert?
I don't know what that means, so.
You should read
This grokking is good.
Okay.
It was great.
I have 4 more questions so far, and I think that it's okay to take the time to do it.
Well, according to the official schedule, we have 9 more minutes.
Oh, well, then, go.
So, I mean, this has already come up.
Wait,
It's
that's
6:30.
that's correct, right?
Yep.
It's 6:30.
So, this has already come up, but I'm curious about an issue that I've worried about as well, which is when you think, so I'm very
Oh,
sympathetic.
no, wait, I'm sorry. We're an hour and 10 minutes for each talk, so we are supposed to end right now.
Right, fuck,
I can't answer that question. We have to stop.
Wait a minute. Okay, as chair of the session, I'm allowing this question.
I'm just gonna make Chris answer it himself.
Now this is all the buildup. I mean, anyway. So I'm very sympathetic to thinking of using the tools of applied math in a much more central way than philosophers usually do. But there's a background concern I have that has come out in a few points in the discussion. Of just, do you think that general relativity is the same theory after we've developed the techniques of conformal completion in order to understand gravitational radiation, or when we've developed the numerical relativity techniques to calculate the waveforms, to compare it to the LIGO data? There's certainly an element of a growth of historical knowledge that's indisputable, but there's a question of whether we can think of that as sort of exploring the content of one and the same theory, or whether you think instead that
No,
as those techniques develop,
I think the
completely-
theory actually grows and develops. I don't think the theory is
okay.
fixed. I don't think there is such a thing as
So it's not that we're
the
discovering
electronic form of
something about the
theory.
implications of field equations. It's-
No, I think the theory actually does, the theory, insofar as one can reify it, really does grow and develop and change over time,
Okay.
given, with, one hopes, improvements in our actual epistemic state.
Yeah, that strikes me as really counterintuitive in a lot of ways, because if you want to think of comparing theories, questions of just even asking what you're doing when you're assessing, again, there's a historical element of the claim that I don't dispute at all, but then I think there are certain questions of, well, what then have you gotten evidence for? It's now, okay, so LIGO gives us evidence for strong field regime of gravitational theory of general relativity. No, it wasn't the theory Einstein wrote down. It's now just a theory that I guess, it's not that the numerical relativists uncovered something which we can use to more fully understand this.
I think these are complicated questions I don't have good answers to. It's not, I would not want to say every single time any individual scientist learns a new fact, the theory has changed. I certainly don't want to say that. But I also don't think I can give you clear, precise criteria. That's part of the point of the talk. I don't think there are clear, precise criteria that one can use to demarcate the theory, even at a given time, even for a given purpose. It's kind of nebulous. And yet, I think we physicists, more to the point, have a good sense of what the theory is, what its scope is, how it can be, good physicists do, appropriately and adequately used. So, and that does change over time, but it's more of a communal kind of thing than any individual thing. I can't give you, another issue here that I just completely glossed over and skated over, and I'm surprised no one's tried to nail me on it yet, is whether all the theories that go into constructing and modeling experiments, which don't seem to be part of GR itself. It seemed like I was kind of slipping them in and saying that they're part of general relativity also, and I don't want to say that. But I don't have I can't give you a good, clean criterion for which part of the experimental model is GR and which part is, Maxwell, is Maxwell theory applied to, applied to these radio antenna or.
Right.
So there are a lot of problems, I think, with a lot of very unclear things with the picture I'm trying to draw. I don't want to claim at all that I have good answers to those kinds of questions yet. I hope to, maybe one day.
So I think we should thank our speaker.
Now what?
I was gonna say, never mind.
Go, my children, be free, have fun, eat, drink.